Hello again, this is Math 2-115, remote delivery for April 16th. And the topic today is binary trees, and I expect there to be two parts to this. Feel free to use this buttons like this to perfect your understanding as we go through with the concepts. An outdoor tree is rooted, and so is the kind of family tree that shows all the descendants of one particular person. The terminology and notation of rooted trees blends the language of these trees in nature and those of family trees. In mathematics, a rooted tree is a tree in which one vertex has been distinguished from the others, and it's called the root. Given any other vertex v in the tree, there's a unique path from the root to v. After all, if there were two distinct paths, a circuit would be constructed. It wouldn't be a tree. So, the number of edges in such a path is called the level of v, and the height of the tree is the length of the longest such path. It is traditional in drawing rooted trees to place the root at the top, as is done with family trees, and show branches descending from it. And so here are more formal statements of those definitions. You may want to pause here just to pick up on all the nuance. I'm not going to read this to you yet again. And a picture is worth many words, and so we can go here and see that we have different levels. And we have relationships with children, parents, and siblings, and descendants, and ancestors, and so on and so forth. So let's see how good we are with these definitions. So you're going to hit pause and answer the following questions. We have a tree with root v0, and it's shown down here. Press pause now, and let's see how you do answer all these questions. Let's see how you did. If you didn't get any of these answers correct, you should go back and rethink it. But I hope that you got these correct. Now, when every vertex in a rooted tree has at most two children, and each child is designated as a left child or a right child, the tree is called a binary tree. So, a binary tree is a rooted tree in which every parent has at most two children. And notice it says at most. Each child in a binary tree is designated either a left child or a right child, but not both. And every parent has at most one left child and one right child. A full binary tree is a binary tree in which each parent has exactly two children. And again, this will appear in some theorems, so make sure you remember that part of the definition. Given any parent, if you have a left child, then the left subtree of V is the binary tree whose root is the left child of V, and whose vertices consist of the left child of V and all its descendants, and whose edges consist of all those edges in the tree that connect the vertices of the left subtree. And there is a right subtree defined in the same way. Again, a picture is worth quite a bit, so you can think about this this picture and pause as you need to or wish to. Now, binary trees are used in many ways in computer science, and one way is to represent algebraic expressions. And so, for example, we have operations and numbers, and in the following labeled binary tree represents the expression a divided by b. The operator is at the root and acts on the left and right children in the root of the root in left to right order. So that is a divided by b. Now, more generally, the binary tree shown below represents a more complicated expression. We have a divided by the sum of c plus d. In such a representation, the internal vertices are algebraic operators and the leaves are variables, and the operator at each vertex acts on its left and right subtrees in left-right order. So the order of operations is represented here. So you can see first you add c plus d, and then you divide a divided by the sum of c plus d. To test your understanding of this concept, I would like for you to pause and draw a binary tree to represent the expression that you see here. Hit pause now. Let's see how you do. And this is the expression that you should have gotten. We come then to a theorem that allows us to calculate the number of vertices and leaves in a full binary tree. So the theorem is stated thus. If k is a positive integer and t is a full binary tree, there's that full binary tree with k internal vertices, then t has a total of 2k vertices. So suppose k is a positive integer and we have a full binary tree and you have k internal vertices. So either it is either the root or not. So if we take the one that is the root, and it's a full binary tree and it's got k internal and they all have to be parents, then what you're going to have is each internal vertex has exactly 2 children, and the number of vertices that have a parent then is twice the number of parents, or 2k. And so what you have is you have 2k, and then you also have the root, which is 2k plus 1. Okay, let's go ahead then and proceed to the next part of this proof. It is also true that the total number of vertices of t equal the total numbers of vertices plus the number of roots. So we're saying that here. So total number equal the total number of internal vertices plus the number of leaves who don't have descendants. This is k by assumption. And the number of leaves, we don't know what it is, but we know that it has to equal 2k plus 1 by earlier. So what we can do is we can solve using algebra, and we'll get that the number of leaves, we'll just subtract k from both sides, is k plus 1. So that is the proof. So now I will ask you a question. Is there a full binary tree that has 10 insertal vertices and 13 terminal vertices? Hit pause, think about the problem, and we'll see how you did. And the answer is no, because a full binary tree with 10 vertices has 11 leaves, not 13. And that's that's the end of part 1. So I will see you in